Now the response of a network can be expressed this way. You have some input. Here's real input. Here's an imaginary input, the way we work with imaginary numbers. And you get an output, and here's the transfer function. So the complex output would be just the transfer function as a function of j omega. And the real part of that, you have the angle of the transfer function in the cosine here too. So we want to know how j omega acts, and we've got some notation, more notation. Phase angle of the transfer, magnitude of the transfer function, and then the complex, the whole shooting match right there. Magnitude and phase characteristics, Bode plots. Plotting the magnitude, we've seen this before. We saw that on an earlier slide. It's the code that I wrote for New Octave. But either you plot the log of the magnitude versus the log of the frequency, or the phase angle versus the log of the frequency. And a lot of people use hertz, by the way. I just want to point that out. It's not always radians per second. A lot of people will make these plots in terms of hertz. So decibel, we've already gone over that a little bit. So here's the definition of a decibel. Has to do with the ratio of powers, log of power times 10. So when we power is I squared R, V squared over R, and putting this in the formula, this is equal to 20. That's why I say 20 decibels per decade of of a simple network. So just using the pre-calculus identity of how the log works, taking this squared outside. There we go. So we can get some pretty efficient approximations to what's going on. So we have this complex formula here for the network function. Ooh, very complex. K naught's frequency independent, by the way. Poles and zeros. More poles and zeros. And the overall function. Properties of the log. That's all this is doing, is breaking this down into properties of the log. So breaking this down into properties of the log, when you take the logarithm of the h of j omega, you're going to get this multiplying term, this power times the logarithm of this. And now here are all the, here's this guy right here. This is a time constant, tau 1. And then this right here is this big fat polynomial here. And there may be others. It keeps going to infinity and beyond. Same thing with the dividing part. Okay, and this is to get some idea of how things work. And remember phase angles, when you multiply phase angle, or that the product of two angles gives you this. The angles do things like this. Two complex numbers. You're multiplying two complex numbers together, the angles add. You divide two complex numbers, the angles subtract. Okay, that's the deal there. So we can get the same kind of idea here, that this is purely, excuse me, this is purely plus or minus 90 degrees. And if it's negative, it's capacitive. If it's positive, it's inductive. And then all these tangents, tangent of this, tangent of all the complex parts divided by the real parts, and so on. It keeps going to infinity and beyond. If it doesn't go to infinity, real networks have a limited amount. We do go to infinity when you're analyzing a cable, for example. We use the continuum approximation, so it can go to infinity. We consider each little, piece of the cable as a resistor and a capacitor in series, and model it like this, just a zillion little things. So we do use continuum approximation to analyze continuous regions. Like this is an example of a coax cable. Okay, there's so much resistance per foot and so forth. Each term. Let's take a look at each term. So this is the constant term. Poles at the origin. It's pretty straightforward. The K0 term, 0 phase angle. This term, 90 degree phase angle, plus or minus 90. This is on a log scale. This becomes a straight line. So on a log scale, there we go. N, how many of these do we have? How many capacitors do we have? Okay, and the phase characteristic, it could be plus or minus, by the way. So this is the example of a negative. Next one's the example of a positive. Simple zero, which we deal with, that's what we've dealt with a lot so far. So we have asymptotic limits. So when this is true, this looks a lot like a constant right here. Yeah. Low frequency asymptote. And the angle, when this is true, well, it's just the what is tangent of zero. Yeah. When it's really big, the approximation is this. And on a log plot that you have, it's linear. It's a straight line. There we go. 20 dB per decade, the decibel business. High frequency asymptote. And then when this is true, that would be the corner where the two asymptotes meet. So we can construct, this tells us the behavior at the asymptote, where 3 dB is, or 7 dB is, or 1 dB is, and so forth. How it curves near the asymptotes. Octave, a factor of 2. Octave, a factor of 2. So this tells us the curvature. And there's the 20 dB per decade. That would be when omega t is bigger. This is the flat line where omega t is small, right here, right here. So you get these asymptotes. Okay. This is the crossover point. Kind of where the two asymptotes meet. And the real curve would be given more like this red curve right here of this network. Okay, let's see. With modern computing, we can pretty much calculate it. So we don't have to construct these by hand so much anymore. When I started, I had to construct these by hand. It was harder in the old days. We had to walk through the snow, uphill, 5 miles, barefooted, both ways to get to school. No, I'm kidding, obviously. So, but MATLAB can make this pretty easy. Okay, and they have a signal processing thing. And New Octave, you got this signal processing thing for free. So a lot of this stuff we can do on computer now. I'm going to end this video here and go to the next one.